Next, we'll talk about Gibbs equations for two very special cases. The first special case is when we deal with incompressible substances, and the second special case is when the substance is an ideal gas. Let's start from the first one. Delta S of an incompressible substance. Okay, what can you get out of the word incompressible? What does incompressible give you? That means the density must be constant. That's the first thing you can get. Density of this substance doesn't change. And then let's recall, we don't usually use density in this class, but the inverse of density. What is the inverse of density? Inverse of density is specific volume nu. So that means nu must also be a constant in this case. If the substance is incompressible, nu must be constant. That's the first thing you can get. And then the second thing you can get is specific heat at constant pressure, Cp, is equal to specific heat at constant volume, Cv, and you can just call them C. Okay, all right, so now we start from Gibbs equation number one. Gibbs equation number one is right here, TdS equal to du plus Pd nu. We start from Gibbs equation number one. TdS equal to Pd nu plus du. And now we can simplify this equation. Why? Because we have derivative nu, and we know nu is constant. Derivative of a constant is equal to 0, so that's why the first term in the right-hand side goes to 0. What is left is derivative of u. And then let's recall, we can rewrite specific internal energy, U, with a function. We can calculate U, which is Cv times T. You can calculate U from this equation, Cv times T. And then we said usually in this class we treat Cv as a constant. So you can take Cv out of it, and then what is left is derivative T. So now what we have is left hand side is TdS, and right hand side is Cv times dt. Okay, so this is an ODE, ordinary differential equation. This ODE is much easier to solve than the original Gibbs equation number one. How do we solve this ODE? Separation of variables. So we move ds to one side and everything that has t to the other side. So it's 1 over t times dt. Okay, so now we integrate. Lower limit s1, upper limit s2. Lower limit t1, upper limit t2. So now left hand side just becomes s2 minus s1, and right hand side has cv, which is constant. You pull it out, and then integral 1 over t dt. What is that? That is natural log t. Lower limit is t1 and upper limit is t2. Okay, so that becomes cv times natural log t2 minus natural log t1. And natural log t2 minus natural log t1 can be rewritten to natural log t2 over t1. So now our final solution is S2 minus S1, which we can just call delta S. The change of entropy is equal to Cv times natural log T2 over T1. So now we're done. You can use this equation to calculate the change of specific entropy, lowercase h. You can use this equation to calculate the change of specific entropy, delta lowercase s, which is equal to Cv times natural log T2 over T1. That's the first special case. And second special case is when you have ideal gas. How do we look for delta S of an ideal gas? Okay, So remember, if it is ideal gas, you can use ideal gas equation. What is the ideal gas equation? Many different choices. For example, PV equal to MRT, that's one of them, or P nu equal to RT, many different formats. We will start from the original Gibbs equations. The original Gibbs equations are TdS equal to PD nu plus du. That's Gibbs equation number one. And Gibbs equation number two is TdS equal to dH minus nu dP. So we start from the original Gibbs equations. And then what we do is we move temperature to the right-hand side. We divide every term by capital T. So right-hand side becomes P over T d nu. And second term becomes 1 over T du. We do the same thing for Gibbs equation number 2. ds equal to 1 over T dH minus nu over T dP. What we did in this step is to divide every term by temperature. Okay, so now what we're going to do now is to rewrite this equation. P over T can be rewritten to what? P over T. If you look at ideal gas equation here, P over T can be rewritten to R over nu. So we can rewrite P over T. And next one, U. U can be rewritten to CV times T, like we said before, and CV is constant. Okay, and same thing happens to Gibbs equation number 2. First of all, enthalpy H. H can be rewritten to Cp times T. And then nu over T. How do we rewrite nu over T? You go back to ideal gas equation here. You can find nu over T can be actually rewritten to R over P from ideal gas equation. Okay, so now let's continue to rewrite those two equations. Left hand side still derivative s ds. Okay, first term in the right hand side becomes R over nu d nu. Second term becomes derivative u. Derivative u can be rewritten to derivative Cv times T. And we know Cv is constant, so you can take Cv out of it, so it becomes Cv times dt. So it becomes Cv times dt and over T. Keep this 1 over T. Okay, so that's the first Gibbs equation. Then we repeat. The second Gibbs equation, left hand side still ds, right hand side, let's rewrite dH first. dH can be written to derivative Cp times T. And then again, Cp is constant, so you take Cp out of it. What is left is Cp dt. And don't forget over T, because here you have 1 over T. Okay, second term, minus nu over T. Nu over T can be rewritten to R over P, and then derivative P. Okay, so now we have the two ODEs. Okay, so now let's solve those two ODEs. How do we solve those two ODEs? Just integrate both left-hand side and right-hand side. Integral left-hand side equal to integral right-hand side. R universal gas constant is not universal gas constant. R is gas constant. R bar is universal gas constant. Take R out of it because it's gas constant, and then what is left is 1 over nu d nu. And same thing happens to the second term. Take Cv out of it, what is left is 1 over T dt. And then repeat for Gibbs equation number 2. Cp is constant, take Cp out of it, what is left is 1 over T dt minus r integral 1 over p dp. Okay, so now this is the integration, and then we can add the limits. Start from s1 to s2, and this is new 1 to new 2. This will be t1 to t2. Same thing again, s1 to s2, t1 to t2, p1 to p2. Okay, so now we can solve this ODE. Left hand side, first one, integral ds, they cancel, so what is left is s2 minus s1, which we call delta s. Okay, first term in the right hand side, r constant, take it. And then integral 1 over nu d nu, that is natural log nu. Natural log nu from nu1 to nu2, that is natural log nu2 over nu1, plus keep CV, integral 1 over t dt, that's natural log t, from t1 to t2, so it becomes natural log t2 over t1. So that's Gibbs equation number 1. Then we rewrite Gibbs equation number 2. Left hand side ds, delta s. First term in the right hand side is Cp times natural log T2 over T1 minus R natural log P2 over P1. So now, if you calculate the change of entropy for an ideal gas, you have two options, and there they are. Okay, but keep that in mind. Choosing an appropriate equation will make your calculation easier and faster. So for example, if I tell you the process is a constant pressure process, which one do you think is easier to use? The first one or the second one? We will probably choose the second one because if it is a constant pressure process, P2 over P1 will be equal to 1, and natural log 1 is equal to 0, so the second term just goes to 0. Okay, very similarly, what if I tell you the process is a constant volume process? Which equation will you choose? Number 1 or number 2? You can probably choose number 1. Why? Because if it is a constant volume process, nu2 over nu1 must be equal to 1, and natural log 1 must be 0, so the first term just goes to 0.